equation in integral form. So what is meant by momentum equation? It is nothing but with the help of physical principle, F is equal to ma, it operates, right? So we have left hand side force term and then right hand side rate of change of momentum term. So what are the forces considered here inside the field, right? So in the left hand side term we have F, right? So this F will be classified into two forces basically, right? One is your pressure forces, right? And then second is your gravitational forces, right? So we have generally it is not pressure forces, generally it is surface forces. So it may be a gravitational forces or else electrostatic forces, okay, electropotential forces. The forces may be in any form, okay. So when we talk about a rheological fluid, we have electrorheological fluid. In that electrorheological fluid, electrostatic forces are happening, okay. So similarly, we have surface forces. These surface forces are again classified into two categories. So one is your pressure force, right, and the other is your shear force, right? So surface forces are classified into pressure force and the shear force. So on the whole, what is F? F is pressure force, shear force, and then gravitational force or electrostatic force. That is any kind of field forces. Okay, this may be any kind of field forces, right? That is external field. So due to external field, we are having some disturbances. The force acting on that by due to that field is called as that field forces, right? And then based on these subcategories, TCF is nothing but pressure force plus air force plus field force. Now what I am going to do is I am going to consider this control volume. Inside this control volume, I am considering a infinitesimal small control volume, right? Let me take this as this infinitesimal small control volume. In this infinitesimal control volume, okay, what I am considering is only the gravitational field. So let F be the gravitational field, that is force acting on the fluid. So let F be the force acting on the fluid. This F is nothing but gravitational force per unit mass. Okay. So when we talk about forces, now we have to resolve all the forces. So that first I am going to solve for gravitational force. Right. For that, my assumption is let F be the gravitational force per unit mass. Per unit mass of the fluid. So if I am considering an unit mass, okay. So in this figure, I have mentioned a unit mass. In that unit mass, F be the gravitational force acting per unit mass. So what I am going to do is I am just categorizing this as what will be the gravitational force there. So therefore, gravitational force acting on the unit element. So gravitational force on the elemental volume. Okay, so I am considering for an elemental volume. So elemental volume of the fluid is density times F times D and then B. So I have mentioned you that this is nothing but volume, right? So for notation, I am writing this V as this form. So dV. So differential of V. So rho F dV is your gravitational force acting on the elemental volume. This elemental volume, right? Along this elemental volume. So in this elemental volume, I have measured the gravitational force. Now on the whole, what will be the net gravitational force acting on the fluid control volume, right? So net gravitational force, what will be the net? So when we talk about net, you have to integrate this term so that we yield the integral form of gravitational force, right? So net gravitational force is right is triple integral over, that is volume integral over V rho F V V, right? So this is your net gravitational force, and let it this be equation number 1, right? And then second thing what I am going to consider is surface forces, right? Second thing is surface force. So how many surface forces are there? Two surface forces. One is pressure, the other one is tau. So what I am considering here is, so pressure, how much is pressure applied on this? How much shear stress is applied on it? So what its direction and its constraint? Okay, we all need to consider it. So for this, I'm considering a small surface, right? Likewise, given in the previous problem, we have a small surface. So in this small surface, pressure is exerted on it. Pressure P is exerted on it. So in this same, shear stress is also exerted, right? So we have pressure and shear stress acting on the surface, right? Now, what you are going to do is that I'm going to write for pressure equation as well as shear stress equation in terms of surface, right? So the pressure which is acting opposite to the inflow direction, so it is given as negative, whereas shear stress which is acting in the direction, in the clockwise direction, so hence it is given in positive, right? So what will be your net surface force, right? So net surface force, the unit of pressure as well as shear stress is Newton per meter square, right? In order to find the force, okay, you have to multiply this term with the area. So this is your surface area ds, right? So what will be your net surface area? So it is surface integral over s minus of p into ds, right? And then plus surface integral over s shear stress into ds, right? So this is your net surface area. Just I have put surface integral over pressure times area, and then surface integral over shear stress times area, right? So this is going to be your net surface force, right? And this is your equation number 2, right? Then what is your total force? That is your left hand side force. So in the beginning I have told you about F. So this F is categorized into 2. We have solved for field forces, that is we are considering only gravitational forces, and then in the left hand side we are considering pressure and shear forces. So all these F has been solved. So what is your F now? So my F is F equal to, right, volume integral over V rho F dV, right, and then minus of surface integral over S P into ds plus surface integral over S tau, yes, this is tau, right, tau into ds. So this is your F and this is your equation number 3, right? So we have solved for left hand side of the Newton second. Now you have to solve for right hand side term. So what is your right hand side term? It is m times dv by dt. So this v is nothing but velocity, right? So a rate of change of momentum. So that is your right hand side term. So m dv by dt. Now we are going to solve for this, right? So for this momentum, you are going to find the rate of fluid which is entering into the fluid. You are going to find the momentum, right? So it is nothing but momentum of the fluid or momentum flux of the fluid. Momentum flux of the fluid entering the So momentum flux of the fluid entering the control surface. Okay, so what is it? So it is nothing but rho v vector dot ds vector. So this rho v vector dot ds vector is nothing but mass flow rate entering into the fluid surface. Okay, so with this term, what I am going to do is you are going to add the additional term, that is v vector, right? So just I am adding the one additional term, that is my v vector, right? Or with this term, okay, momentum flux along a small control surface I am applying. So let this be a small control surface ds vector. With this ds vector, I am considering a single velocity vector v vector. So what is my momentum flux is? So here we have m. Okay, so m is nothing but mass. So for that mass, I am considering the mass entering into the fluid, that is rho v vector ds vector, okay, times v vector. So here on the whole, we are considering a overall control surface, so that you are putting triple integral over this term. So double integral over this term, that is surface integral, since the differential is differential function is with respect to surface, right? So we have find out the momentum flux of the fluid entering the control surface. Okay, similarly you have to find the transient steady. That is, transient steady means, so with respect to time the fluid changes. Okay, the fluid and its property changes, so with respect to time. So you are also considering the other term, so with respect to time. So for this you need to analyze the transient momentum. Transient momentum of the fluid right, inside the control volume, So for this, what I am considering is again the same term, mass multiplied by velocity, right? So what is your mass? Mass is nothing but rho into dv. So this is mass. So density into volume, which will gives you mass, right? And then velocity, right? You are multiplying with v vector, right? And then you are introducing what? The time derivative, right? So I am introducing the time derivative, that is dou by dou t. So dou by dou t of triple integral over control volume. Okay, so this is your equation number here. For momentum flux, you are making it as equation 4. For transient momentum flux, you are making this as equation number 5. So your m dv by dt, that is your right hand side term, possesses two characteristics. One is your momentum flux due to the control surface, and then transient momentum of the fluid practice inside the control volume. On the whole, we have the transient vibration or transient variation of the fluid properties inside the control volume. So on the whole, we are measuring dou by dou t triple integral over v rho dv v vector, right? And this is your equation number 5, right? So finally, what we get? So as per equilibrium, as per forces in equilibrium, that is f is equal to mass into dv by dt, right? So by this, you have to put equation number 3 is equal to equation number 4 plus 5, right? What is your equation number 3? My equation number 3 is, we have this, right? So triple integral over v, rho f into dv, right, minus of over s p into ds plus surface integral over s says just tau into ds equal to, what is your equation number 4? Surface integral over s rho v vector dot ds vector times V vector, right? And then plus volume integral over, right, rho by dou t, volume integral rho V vector dV, right? So this is your momentum equation in integral form. So this gives your momentum equation in integral form. Then we are going to see about momentum equation in one dimensional form, right? So I am considering the same equation, okay, and then we are having some assumption for one dimensional form. So what are the assumptions? So one dimensional compressible momentum equation. What is it? Right? So for these assumptions are there. So you are treating the flow as an inviscid flow. Right? So treating the assumption as inviscid flow, and your second assumption as one dimensional. So here only in one direction we are going to consider, right? We have one dimensional control volume, okay, which we had discussed for continuity equation. The same one dimensional control volume is taken here. So one dimensional control volume model, right? And then the flow is treated as steady, right? That is inviscid flow and the steady flow. So there are two important assumptions, and then one dimensional control volume is taken into account, right? And then no field forces. No field forces. So field forces means there is no electrostatic forces or electromotive forces or else gravitational forces. Okay, we are having only a single force, that is only the pressure force, and we are not going to consider about the shear force of that, because since the flow is inviscid flow, shear force is neglected. How is neglected, right? And since it is one dimensional control volume, we can write for one dimensional control volume for the same equation. And then steady flow means this dou by dou t, that is time derivative, is neglected, right? And then no fluid forces means, and then body forces, that is gravitational forces, right, are neglected, right? So these are the constraints, okay, or assumptions of for one dimensional compressible momentum equation, right? So with this, keep in mind, okay, so we have this momentum equation, okay. Now what we are going to do is, for make this particular equation into one dimensional form, we are going to neglect two terms, that is you are going to neglect force term, we are going to neglect shear stress term, we are going to neglect time derivative term, since the flow is steady, okay. So we are considering only the left hand side a single pressure force, and then right hand side only the momentum force, right? So what could be your final equation in three-dimensional form? It is minus surface integral over S P into ds is equal to surface integral over S rho V vector dot ds vector times V vector, right? Right. Okay. So this is your rectangular control volume for one dimensional case. Now we are going to substitute this rectangular control volume for our consideration, right? So for this, what I am going to do is, so minus of, right, and then we have P into ds, right? So P into ds, so minus of this term, and then we have inflow term and then outflow term, right? So zone number 1 is your inflow term, right? And zone number 2 is your outflow term. So for inflow, all the parameters are set to be negative. So minus of P1. So what is the pressure in the first zone? It is P1 into A, right? We have the area. So just put A. This A is nothing but constant area, so that you are putting A here, and then plus for what is for outflow? For outflow, all the parameters are positive, so it is P2A, right? I am just substituting for inflow term, left hand side term as negative and right hand side term as positive, right? And similarly, I am going to do it for this term. So density, velocity, area, again velocity, right? So what could be your inflow? So for inflow, all the term is negative, so minus of for density rho1, and then for B vector U1, and then for BS vector A, and then for V vector U1, right? And then you are following the same for outflow. So, but for outflow, it is positive, right? The term is positive. So, plus rho2 U2 A U2, right? So, you just multiply this negative term inside, right? What we get? So, we have P1 plus P2 of A, right? So, P1 not plus P2, it is minus P2 of A is equal to, here is also you are taking A common outside, so you will get minus of rho1 U1 square plus rho2 U2 square, right? So we are getting this, right? So cancelling out A and A, rearranging this equation, what we get? So P1 plus rho1 U1 square is equal to P2 plus rho2 U2 square, right? So this is your one-dimensional momentum equation, right? It's very simple. Okay, we are going to use only this continuity, momentum, and energy equation for solving all kinds of compressible flow equation, right? So we need these state equations or governing equations for all kinds of shockwave flow problems, right? So you have to keep in mind, if I am asking about one-dimensional continuity or one-dimensional momentum or one-dimensional energy equation, you should have some idea on this, right?